Good evening. I'm Jack Lyrica.
I'm Dan Itkin.
I'm John Numi.
I'm Garrett Organic.
And we are
Team Name. On March 21st, 2011, the Fukushima power plant failure resulted in widespread contamination in the immediate area as well as all over the world. The most concerning radionuclides that were emitted from this disaster were iodine-131, cesium-134, as well as cesium-137. One of the largest areas of concern is the contamination of reservoirs for drinking water. Given a reservoir for 400,000 people, it was calculated that 33.2 million gallons of water per day are required, based on 83 gallons of water used per day per person. Assuming that the groundwater radiation is equal to the reservoir radiation and that the levels of contamination are constant, the current contamination levels are 400 becquerels per meter cubed of iodine-131 and 53 becquerels per meter cubed for both cesium-134 and 137. However, these numbers are lower than the legal limits, which are 400 becquerels per kilogram of iodine-131 and 200 becquerels per kilogram for cesium-134 and 137. Thus, the goal of our unit operation is complete removal of radionuclides.
To reach this goal, we considered several methods of radiation abatement. Our first solution was reverse osmosis to remove particles based on the principle of size exclusion, though this process is lengthy and is better implemented for small-scale operations. Next, we considered using an ion exchange technique to form radionuclide compounds, which would then be filtered through a series of charge grades. However, this process requires strict pH regulation. Finally, we contemplated a granular activated carbon system to remove our radionuclides. Though a simple removal process in theory, granular activated carbon can effectively remove positive radionuclides and is also able to be reused.
To treat the radioactive contaminated water, we decided to use a granular activated carbon filter. We chose this specific unit operation because granular activated carbon is relatively cheap and readily available. The activated carbon is created from a char of organic material by the process of pyrolysis, which gives it its porous qualities and high surface area. The high surface area allows for very efficient filtering through the processes of adsorption. The carbon in the filter has an inherent negative charge, which makes it effective at attracting the cesium cations.
Adsorption is the process by which molecules or ions that are present in one phase start to condense and concentrate onto the surface of another phase, so the large surface area of granular activated carbon will increase the efficiency of this process. Contaminated water is first transported in bulk into the carbon filter, then diffuses through the pores and surface where it is either chemically bonded to the carbon or physically stopped by micropore size exclusion.
The sheer volume of water that needs treatment requires us to implement 24 of these carbon filters in both a parallel and series orientation, with 12 filters in each parallel set. Both sets of parallel filters will contain the standard granular activated carbon and will aid in the abatement of the positively charged cesium. These filters each have a calculated bed life of just over 13 hours. They are arranged in series so that half of these filters may be removed for reactivation, while the other 12 maintain the capability of removing the cesium, thus sustaining a 26-hour cycle. These filters will be placed following both clarification and flocculation in the treatment process, therefore influence suspended solid concentration will be minimal and can be represented by our radionuclide concentrations. Our design considerations include flow rates, tank dimensions, radionuclide removal rates, and carbon bed life. The average operation time of carbon filters ranges between 100 to 600 days. The effective adsorption zone is a constant length but moves down the column as the carbon front is used up. We define the time at which the adsorption zone reaches the bottom of the carbon column as the breakthrough point, at which time the carbon must be replaced or reactivated. Carbon can either be regenerated through volatile oxidation and steam cleaning or reactivated through rounds of intense heating. We plan to use the regeneration process to remove the cesium ions from the contaminated carbon, as a repetitive steam cleaning process will effectively remove the heavier cesium ions from the contaminated carbon.
For our calculations, we had to make a couple assumptions. First, because the initial concentrations are below the legal standards, we are assuming complete removal of our contaminant. Next, we are assuming the contamination is at a constant level. Last, we also decided to not factor in the degradation of the radionuclides as they pass through our filters, because if our system can handle the maximum mass of contaminants, it includes a factor of safety in reality. Some of our other assumptions are as shown.
As the aforementioned concentration levels are measured in becquerels, it becomes necessary to convert to mass-based units. This is possible by simply multiplying the half-life of each respective element by the concentration in becquerels and converting to grams via molecular weight values. The resultant concentration are as shown.
For our preliminary design considerations, we first determined the number of each type of filter required to handle our given flow rate. Using these equations and specified ranges for general tank dimensions and capabilities, we determined a demand for a total of 2 sets of 12 granular activated carbon filters so that one set can be operating while the other is regenerating.
based on a short bed life of about 14 hours. Each tank will be roughly 30 square meters in diameter and 7.5 meters in length.
Another important design consideration is the effective bed life of the carbon in both filter types, which can be solved for using these equations. As you can see, by relating the volume of treated water to the flow rate, it is possible to determine the expected life of the carbon. This value will dictate our overall radionuclide removal rate, as the contaminated carbon will then have to be safely housed for the duration of each radionuclide's respective half-life, or be otherwise disposed of.
This table shows the results of our calculations. As you can see, we found a carbon usage rate of about 1320 grams per meter cubed, which tells us how much carbon is required per meter cubed of influent water. We also determined a bed volume of about 218 meters cubed with an empty bed contact time of 30 minutes.
While our unit operation would likely prove adequate in a real-world application, there are many ways on which to improve it. Ideally, an experiment would have been performed to create a Freundlich isotherm model to determine the necessary coefficients in order to most accurately calculate the ratio of carbon to cesium needed for complete removal. The number of filters in parallel could also be increased to increase the bed life of each series, as our 13-hour cycle would most likely prove ineffective cost-wise. Increasing tank dimensions would also have the same desirable result. Moreover, this unit operation could be expanded upon to remove the negatively charged iodine-131 isotopes. This could be done by impregnated granular activated carbon with certain metals or metal compounds, such as silver or potassium iodide. This impregnation effectively changes the charge of the carbon so as to capture the iodine anions. These impregnated filters would then be placed following our designed filters in series so as to remove both cesium and iodine isotopes.